Right, so I'm here with question 3 of the 2022 MOI Individual Statewide Test, and here we're asked to compute the limit of a given summation. Now, upon looking at this, you should automatically try to think of how we can convert this into an expression that is far more computable and easier to work with. And one way we can think of doing this is by interpreting the summation in this expression as a Riemann sum, which we know is an approximation for an integral. So that's going to be our goal, is to convert this expression into an integral which we can actually compute. Now, why does this work? Well, let's say we have, for instance, a function and we're trying to find the integral from a to b, and we know we can approximate this using a Riemann sum. We simply have the area of numerous rectangles under the curve, and that will give us a solid approximation. And let's denote the number of rectangles as n. What we see here in the limit, n is actually approaching infinity, and that's really advantageous for us, because if the number of rectangles we're approaching is infinity, that essentially means that the sum is going to be equivalent to the definite integral. So that's going to be our goal, is try to convert this into an integral. So let's just rewrite the question. We have the limit as n approaches infinity of the given summation. Now you may see a problem with this 2n because typically we work with an index that is merely a variable and doesn't have a coefficient, but I will show a workaround this. And then we have n over I squared plus n squared. So what I'm first going to do is factor out this n squared from the denominator to get this into a format that is easier for us to work with. And I'll show you why this works and what is the significance of this. So again, we have the summation, I equals 1. Whoa, that looks like a 0. I should rewrite that. So our denominator stays the same, and we're going to factor out that n squared. So this is going to leave us our I squared will turn into I over n squared, and of course we also will have a 1. This works because when we multiply n squared times this variable, we will come back to this I squared here. So the expressions are equivalent. Now you may notice that now we can actually cancel out the n and the n squared. So we're going to do just that for the sake of simplification, and also to get us to our next step. So I'm actually not going to write the integral, I'm just going to write our expression for the sake of time. So we have 1 over n of I over n squared plus 1. Now we can factor out this 1 over n from this expression and put it at the front of our summation. And I'll show you where this leads to in a second. So I'm actually going to rewrite the limit here. That looks like an m, but I promise it's an n. So we're going to have that 1 over n at the front of our summation of 2n over I equals 1. Then our n is going to be gone from the denominator, so we're just going to have I over n squared plus 1. Now, as you may recall from the Riemann interpretation of a definite integral, we must have a term such that b minus a is over n. Now graphically this makes sense that we have to have this somewhere within our expression, because let's think back to our graph. Say we have a given function confined from a to b, and n represents the amount of rectangles we have. The b minus a represents the distance between these 2 points, and the n represents the amount of rectangles we have, which in this case is again approaching infinity. So essentially determining what this expression is will help us determine the bounds of our integral. And we see that we have something similar to that. We have this, and we also have a factor, except our numerator isn't a difference of two constants. So let's rewrite it such that it is, and that will help us determine the bounds of our integral. So how can we do this? We can rewrite this 1 over n as 2 minus 0 over 2n. This works because the 0 will just cancel, and we could also cancel the 2 and the 2 from the 2n, and this will again simplify to 1 over n. So the expression is still equivalent. And then we have our summation, of course, and you may notice something here is that the 2n here, the 2n here and the 2n in this denominator match. And that's really great for us because now we don't have to make any substitutions for our index in order for this to work. We've rewritten this such that it is an expression of 2n instead of n. Then we have the I over, let's just move this. Make this smaller. All right. Another thing I'd like to point out is this term with the I over n is what is known as a dummy variable. And this basically means that this is the term that is going to replace, be substituted as x for when we create an expression in terms of x for our integral. So I'm starting to run out of space here, so I need to make this smaller. Okay. So again, the I over n is going to be substituted for x, so we can make a function of x for our integral. Now back to our integral. We see that here we have 2 minus 0, and this is actually great because these denote the boundaries of our integral. We have let me write this with the pen. A is equal to 0, whereas b is equal to 2. Now we can begin constructing our integral. And so we have the integral from 0 to 2 of the function 1 over, again, now we're going to use x from our dummy variable in the previous expression, plus 1 again. And you may notice that this integral is actually the identity for arctan. So let's rewrite it here. This will reduce to arctan of x from the bounds 0 to 2. So now we can just compute this as normal. We have arctan 2 minus arctan of 0, which you may know is simply 0. Therefore, we are left with our answer of arctan 2 as our final simplification. So if we go all the way back, this should be answer choice B.